In this video, we're going to solve the same exact problem that we did last time. In fact, I'm cutting and, well, I'm not pasting, but I'm cutting and putting. Same exact problem, but now we're going to use a different system. We're going to make probably would use a system that I would have come up with anyway. Okay, so same exact problem. We want to know how fast does the cart go. Everything's the same. There's 100 joules of elastic potential energy in the spring. The cart has a mass of 2 kilograms. It's initially not moving. The spring pushes it. And then I want to know how fast does the cart go after it leaves the spring. Friction is negligible. We don't have to worry about any kind of thermal energy. And that is not black. Do I need black? Yes, I need black. All right. So I can't remember exactly how I do the steps here, but one of the first things you need to do is think about after you decide, I got to use conservation of energy because this force isn't constant, I can't use Newton's second laws, is to think about, okay, what's going to go in my system? You can put anything you want in your system, and I would just encourage you to use, at least for now, use what makes your life easiest. And I see a spring and I see a cart, and so I'm just going to go ahead and say, I want the spring and the cart to be part of my system. Okay, now let's see, what did I do in the last one? I can't remember. So I'm going to pause the video and get my thoughts together. I don't think my thoughts are together, but close enough. Okay, so now let's think about what is conservation. What is our statement of conservation of energy in this particular context? Okay, so let's just do a little side note here because, so the most general statement says, the energy in your system plus any energy that comes in equals the energy in, let's call that like an A, then the energy in your system at some later point in time minus energy that leaves because it goes out. This is basically a complete statement of conservation of energy. Well, at least doesn't involve heat, but anyway, for our chapter, this is a chapter 10 complete statement of conservation of energy. Okay, so basically it says if you have no external interactions, then what does it say about the energy in your system? It says basically, if I don't have work on my system, or if my system doesn't do work on something else, then whatever energy is in my system is going to be the same over time. And that's exactly what's going on here. Okay, because I've included the spring in the system as well as the cart, then this is no longer a situation where the spring does work on the cart. When the spring pushes on the cart, that is an internal interaction. So rather than seeing work being done, there's going to be an energy transformation, and there never was any work out. Okay, so what we're going to do is we're going to say then that the total energy in my system at A, and this is now the spring is part of my system, is going to equal the total energy in my system at B. No work, so there's no change in the energy. Okay, well, let's do that energy inventory and think about what forms of energy are present in my system. And I'm not going to write them all out. We've got E-therm. Okay, that's not going to happen here. So I've got gravitational potential energy, I've got elastic potential energy, and I've got kinetic energy. These are my 4 potential forms of energy. Okay, what is in my energy at A? Do I have anything? Is anything elevated above a low point? No. No gravitational potential energy. Is there any spring energy? Yes, absolutely. So there is spring energy at A. Okay, is there any kinetic energy? Nothing is moving. So the total energy in my system at A is going to be the energy in the spring at A. Okay, what about at B? Let's go through our energy. Okay, no gravitational potential energy because nothing's going up or down. Is there any spring energy? Now, you say the cart's here, but it still includes this spring, but the spring is sprung. Okay, so by the time the cart leaves the spring is back to its natural state. It has no energy, so there's no spring energy anymore. But there is motion, and so there's going to be kinetic energy, and we're going to say that's the kinetic energy at B. Okay, well, this is just like, the only difference is instead of calling this work in, this is the energy in the spring. So this is 100 joules, and this is going to be 1/2 mv at b squared. And we've already solved this problem once. So maybe you should do it yourself because I want to keep this video short. And we can see we'll get exactly the same answer, which must be the case because nature doesn't care whether you include the spring or not in the system. You have to get the same answer, and we did. Okay, so this is just one example where it really doesn't matter what you include in your system. Sometimes including something in your system may make the problem a lot easier. We'll talk more about that in a future video. Sometimes it doesn't really matter at all, but in this case, it didn't matter. Okay, but go ahead and include a part of your system. Why not? Okay, bye.